Welcome to lecture 9.2, in which we will start to talk about data structures, or in Hebrew, מבני נתונים. Now, there are two basic or elementary data structures. One of them is the array that we've seen in the course in many different examples. And another data structure, which is similar but not identical, is sometimes called a list and sometimes also called a linked list, or in Hebrew, רשימה or רשימה מקושרת. Now, both of these data structures have advantages and disadvantages. Some of them, or the array is better for searching, for example, but not so good for insertions and removal of elements. מערכים הם מאוד נוחים לחיפוש, פחות נוחים לתחזוקה. On the other hand, the list data structure is not very good for searching, but is excellent for insertions and removals. הרשימה המקושרת פחות טובה לחיפוש, אבל הרבה יותר טובה לתחזוקה, כפי שעוד מעט נראה. So in some cases we use arrays, in other cases we use lists as the application requires. Now, in computer science, we have many abstract data structures, data structures which are more abstract than arrays and lists. And here are some names: sets, stacks, queues, maps, trees. These names don't mean much. I guess set does mean a lot because you study sets in mathematics, but the others are probably new concepts for many of you. And don't worry about it. We will spend some time talking about it, about these data structures in the next lecture. And you will spend the whole semester talking about these data structures in a course which is called Data Structures, or in Hebrew, מבני נתונים. Now, the cool thing about all these data structures is that typically we implement them using either arrays or lists. And that's something that we will see in the next lecture. In this lecture, I want to dedicate the whole lecture to discussing the art of creating and maintaining linked lists, or simply lists. So that's what we'll do throughout this lecture. So what is a list? We can think about a list as an ordered collection of elements. And there are many examples of lists: shopping lists, course lists, playlists, guest lists, and so on. And in every one of these lists, we want to do a bunch of basic operations, like creating a list, inserting an element, searching the list for an element, removing, updating, and so on. So these are the basic operations that we want to support. So how should we do it? Well, if we have an array and we want to maintain the list in an array, then the elements will be stored in a sufficiently large array. For example, I can assume that, when I go to the supermarket, I never have more than 100 different things to buy. So I will always allocate an array of 100 elements. I will call it S-list for shopping list. And I'm not going to allow gaps in the array. So you will notice that to insert an element in a specific place, let's say if I want to insert an element between milk and eggs, I have to move eggs one position to the right. This is inconvenient, and it may take a lot of time, because I may have many more elements after eggs, so I have to move every one of them one position to the right. So inserting an element is hard work. And also deleting an element. If I want to delete milk, I have to move all the elements on the right to the left, because I just decided that I'm not going to have gaps. So maintaining the array is not fun. On the other hand, I can use a linked list implementation, as we see here. And here, the list consists of what we call in English nodes, or in Hebrew, tzmatim. Every one of these nodes has a value, like bread, milk, eggs, and it also has a pointer to the next node in the list. Now, if this is your list architecture, it is very easy to insert or delete an element anywhere you want. You can do it as a local manipulation without disturbing the rest of the list. אם אתה משתמש במבנה נתונים כזה, כדי לשמור את הרשימה שלך, אז להכניס צומת או להוריד צומת בכל מקום שהוא, זאת פעולה מקומית. אתה עובד עם הפוינטרים, אתה לא מפריע לשאר הארכיטקטורה של הרשימה הזאת. The result of this setting is that we have an elegant, what is known in computer science, abstract data type, ADT, that comes to play in numerous applications in computer science. And that's why it's so important to talk about lists. And why is this abstract? Because there are many details going on behind the scene, as you will see throughout this lecture. So a list is a dynamic data structure that can grow and shrink as you want. You don't have to decide in advance how many elements you will have. So it's a very convenient and elegant thing to play with. All right, so here's a list of 3 elements, bread, milk, and eggs. And here's the abstraction. The list can be empty, which means that slist, my shopping list, will point to null. If it points to null, it means that I have an empty shopping list. And each node contains 2 fields, a value field, like bread, milk, eggs, and a next field, which is the name of the gray field, so to speak, which is a pointer. And the last node, as you see, points to null. This is this graphics that I did at the end of the list. אז רשימה זה אוסף של צמתים, כל צומת יש לו 2 שדות, ערך, שאני קורא לו value, ופוינטר או מצביע לנוד הבא, שאני קורא לו next. Now, how can we implement this list? One way to do it is to create a class called node, and each element in this list that you see here will be a node object. And I'm going to link these nodes together and create what you see here in the picture. Now, the low-level implementation of this list will be a set of memory blocks which will be scattered somewhere in the RAM. Scattered in Hebrew is mefuzar. Okay, so how will it look like? It will look something like this. So this is a low-level implementation of the list that you see at the top of the slide. So let's see what is going on here. By the way, all the addresses here are arbitrary, or in Hebrew, shrirutiyim. They are just for illustration purposes. So slist is a pointer, and it has a value. The value, as we see, is the address 45,123. So we go to this address, 45,123, and we find bread. Great. Now the next word in the memory is a pointer. This is the next field, which is 45120. We go to 45120, we find milk. And next to milk, there's a word with an address, 45125. We go to it, we find eggs. And the next word is null, which means that we are at the end of the list. So as you see, the nodes are all over the RAM, and yet if you just follow the pointers, you can completely construct the list and use it as you please. This is a great example of the difference between an abstraction, which is how we think about the list, and an implementation, how the list is actually realized or implemented in memory. By the way, the memory has a special area called a heap, and that's simply the area in which Java stores arrays and objects. It's a very big part of the RAM, and that's where all my matrices, images, points, sets, all the stuff that I create as arrays and as objects will be stored in the heap. All right, so that's the abstraction and implementation of a linked list. Moving along, here's an example of how we can use a list for some productive purpose. So suppose we want to build a word processor, like Word, for example. How can we do it? Well, we can decide that the basic data structure that we are going to maintain is going to be a linked list that contains all the words that we type into the document. So the beginning of the list is a pointer called txt, and we see that if we will simply follow the pointers, we will get the text or the user's view. It was the best of times. That's what the user sees. Now let's say that the user comes in and wants to remove the first two words. That's what we do when we do word processing, right? We mess up with the text. So you mark the first two words and you click delete. What happens behind the scene? Well, something very elegant. All we have to do is move the txt pointer to the third word, which is the. So now when the user says, show me the document, what you will see is everything that begins at txt, which is the best of times. So effectively, you knocked out the first two words in the document. All right? By the way, this also shows you how you can do undo, right? How you can decide to undo the delete and go back to the original. But that's a different story. All right, now let's decide, suppose that the user now wants to replace the word worst with, to replace best with worst. So the user marks best and types something instead. How are we going to support this operation? Well, we'll do something like this. We'll create a node called worst, and we will link the previous node, instead of linking to best, we will now link it to worst, and we will link worst to of, and effectively speaking, when the user will look at the document, she will see the text, the worst of time. We simply follow the pointer. So best is no longer relevant. אנחנו פשוט עוקבים אחרי המצביעים, מתחילים מ-txt, הולכים ל-the, המצביע הבא מראה ל-worse, המצביע אחרי זה מראה ל-of, ולכן עקפנו את best. best עכשיו הפך להיות לחלוטין מחוץ למשחק. So you see that this notion of a linked list is extremely effective and useful for some applications. And obviously in a word processing program, the basic value will not be a word, but rather a single character, right? Because I want to allow to erase, insert, and so on, single characters and not necessarily complete words. All right, so enough motivation. I'm sure that you're now convinced that that lists are important, an important data structure. And let's see what comes ahead. So I'm going to discuss two different ways to implement lists. The first way will be simple, primitive, and crude. Crude in Hebrew is pashtani, gas. But we'll do it because it will give you a good feeling of how to work with the pointers, which is very important when you build lists. The second implementation will be what what we really have to do. I'll show you a nice, safe, good implementation of lists using something called the list package. And by doing this, I will also introduce a new subject to this course, which is working with packages. All right, let's start with a node class implementation. And here's the node API. It's a class that represents a node in a list of strings. A node has a string value and a pointer to another node, as you remember from my pictures. Now I'm going to have two constructors. One constructor will get a value and a pointer, which is an address in memory. And it will create the node that contains this value and this pointer. Notice that this data structure is recursive. It's recursive in the sense that the second element that I called next is itself a node, right? So the node object contains another node, which is, the tail, the next node in the list. And I'm going to have another constructor. Just to make my life easy, I will also allow to create nodes that have no next parameter. If I don't specify a next parameter, I will create a node that points to null. Okay, this is the last node in the list, or sometimes I will need it for other purposes. So I have two ways to construct nodes, one with a pointer that I'm going to specify, and another with a null pointer. And finally, as usual, I'm going to have a toString method that simply displays this particular node. It actually displays only the value of the node. We don't care about the pointers. All right, so here's an example of client code that uses this class. So we create two node variables. These are object variables of type node, A and B. One contains it, the other one contains was. And notice that in both cases, I'm going to call the second constructor, right? I did not specify, I specified only one argument. So I'm going to invoke or call the second constructor, which is going to give me these two nodes, right? I have two nodes that are disconnected from each other. There are two pointers, A and B, that point at them, and both nodes have a null next field. Okay, both nodes point to null. All right, moving along. Suppose that now I do the following operation, A.next equals B. This means set the next field of A to the value of B. Well, the value of B is the address of the second node, right? So effectively, I'm going to get this. So by this little statement, I connected the two nodes together. All right, suppose now I create a node variable called T1 and I set it to A. Well, A is an address. So now I have another node variable pointing to it. So I have this setting. Okay, so now I can get into the list using either A or T1. Well, now I do something that looks a little bit complex, but not really. I create a new node. The value of the new node is going to be the text the, and the tail, the next, will be yet another node that begins with the value best and ends with null, right? So this is actually, it's an interesting statement what we see here, because the outer node calls the first constructor, because we provide both a value and what is going to be an address in memory. So we call the first constructor. And the inner node calls the second constructor, because we provide only a value. כמו שאתם יכולים אולי לראות, הסטייטמנט הזה שהוא קצת מורכב, יש בו שתי קריאות לקונסטרקטורים. הקריאה החיצונית, הנוד השמאלי יותר, קורא לקונסטרקטור הראשון, כי הוא מעביר לו גם ערך the, וגם כתובת בזיכרון, שזו תוצאה של הקריאה לקונסטרקטור השני. אז בעצם אני קורא לקונסטרקטור הראשון. לעומת זאת, הקונסטרקטור הפנימי, הקריאה לקונסטרקטור הפנימי, קוראת לקונסטרקטור השני, כי פה אני נותן רק ערך, ולכן אני מצפה לקבל null בסוף. What will be the result? Well, it will be simply a new list that begins with T2. And so, in one statement, I created a list that consists of two nodes. And then I do T.next. Sorry. T.next equals T2. Okay? So what's going on here? Well, T1.next, let's look at the picture. T1.next will give me the address of the second node in the list, which is best, right? And then I take the next element of this second node and I set it to T2. Whatever is the address of T2, I'm going to set it to the next element of best. And therefore, I will get what we see at the bottom, right? I basically connected the two lists. I connected T1 with T2, and we're all set. All right? So if you're not sure that you understood this example, I request that you stop the tape, look at it for another 2 or 3 minutes, convince yourself that you understand what's going on, especially look at the statement T1.next equals T2, and figure out for yourself what is going on. All right, so let's look at the implementation of the node class. How did we make it happen? Okay, so here is the inner view of the node class. First of all, we're going to create objects that have two fields. The first field is simply a string, like the word eat, was, bread, milk, whatever. And the second field is going to be a node, an address in memory, which we call next. And you see, just by looking at what I showed you so far, you see that this is a recursive data structure or a recursive object, because one of the fields of the objects is itself another object. Now, what is an object? An object is an address in memory. So that's the implementation of the next field that points to yet another node element. Now I realize that this is a little bit tricky, and it's a step ahead in sophistication in this course, but we're getting to beginning to get to the end of the course, or to the last third of the course, so we have to shift gears and talk about more challenging things. So this is a recursive object definition. Now, first constructor, as you saw, takes a value and the next argument, a parameter, and next is simply an address, okay? So, all we have to do is take these two values and put them inside the fields of the objects, and that's exactly what they do. This value equals value, this next equals next. All right, what about the second constructor? The second constructor gets only a value, right? So what we want to do is create a node that has a null next. And we can do it if we will call the first constructor and pass to it the two parameters value and null. If you will look at the previous lecture, you will see that a constructor can call another constructor using the magic syntax this, open parentheses, and that's an example of code reuse. We could have said this dot value equals value, this dot next equals null. It would be the same effect. But I prefer to call my other constructor because in reality, the first constructor can do a lot of, many more things, and I don't want to repeat all this code in the second constructor. All right. What about toString? toString simply gives me the value of the node, so I'm going to return the value because the value, excuse me. Well, I did hear something which is unnecessary. When I wrote the code here, I thought that value was an int, so I concatenated it to an empty string to make it a string, but it's not really necessary because the value is a string. So no harm done. We can leave it like this, but it's unnecessary. I could have just said return value. עשיתי פה איזושהי טעות טיפשית, אני חשבתי ש-value, כשכתבתי את זה חשבתי ש-value זה int, בעצם value זה string, ולכן הקאסטינג הזה פה הוא מיותר. הייתי פשוט יכול להגיד return value, וזה היה בדיוק אותה תוצאה. Alright. Now, what else can we do? Here are some more examples of working with this primitive list. I create a node with the value of A. Now, look what I wrote in the documentation. One way to think about this is that what we have now is a list consisting of the value A. We can think about this as the head of the list, and a tail. And the tail is null, right? זאת רשימה שיש לה ראש וזנב. הראש זה הערך A, והזנב זה כלום, null. That's what we have so far, okay? Now we construct another node that consists of the value B, and the tail is Q. Now what is Q? Q is the previous list, right? So now we have a list that starts with B and ends with the list that we had before. And we can keep playing this game. We can create another node called C and connect it to Q, and now we'll have the list that we see on the right-hand side. That's another example, a very vivid way to see that a list is a recursive data structure. Because what is a list? A list is something that starts with a value and ends with a list. What is a list? A list is something that starts with a value and ends with a list. I can go on infinitely and say what I have here because this is a recursive data structure. זה מבנה נתונים רקורסיבי, כי זה מתחיל באיזשהו ערך וממשיך סליחה, מה זה רשימה? רשימה זה דבר שמתחיל באיזשהו ערך כמו C וממשיך עם רשימה. מה זה הרשימה השנייה? היא מתחילה עם איזשהו ערך כמו B וממשיכה עם רשימה. מה זה הרשימה הבאה? זה A, ממשיך ברשימה. מה זה הרשימה הבאה? null. הסיפור נגמר פה. אבל זה יכול להיות גם רשימה של מיליון איברים. אוקיי, אז זה מבנה נתונים, כאמור, שאפשר לחשוב עליו בתור מבנה נתונים רקורסיבי, שמוגדר בעזרת עצמו. Okay, that's what we'll end up having in this example. We have a list with a pointer Q pointing at its head, and we have the values C, B, and A. Great. Now, suppose we want to print the list's elements. Well, one way to do it is to use this code here. We begin by creating a node object called current, and we set it to to Q. So we're going to have this object variable called current. I wrote CURR to save some space. So current now points to the first element in this list. Okay. Now let's look at the while loop. If current is not null, and it's not null because it points at a node, right? So it's not null. If it's not null, then print the value of the current object. So I'm going to print C and the space. And then current equals current.next. Current points to a certain node, and when I say current.next, I will get the value of the next field of current, and effectively I'm going to have this. Now this is still not null, so I'm going to print now B and a space and move current forward. It's not null, so I'm going to print A and a space and move current forward. When I will move current forward, look what will happen. Current equals current.next. Well, current.next is null. So finally, I'm going to get out of the while loop. And this will be the end of the story, and I will end up printing CBA. All right? Great. So, the benefits of this very simple definition of a list is that it's very flexible, very easy to... On the one hand, it looks like it's easy to work with because I can do whatever I want. It's very direct. I have complete control of the list. But there are also some big-time disadvantages. It's actually hard to use because, whenever I want to go through the list and do something, I have to write code that does it. I'm the client. I'm the programmer who wants to use lists, and look how much work I have to do in order to move in the list and do something. I have to write loops, and that's a simple thing. Suppose I want to delete something in the middle of the list or whatever, I have to do hard work as a client. I would expect the person who wrote the list implementation to give me these capabilities. I don't want to do it on my own. Also, the setting here is very unsafe. It's unsafe because any client programmer can mess up the pointers of this list because we have direct access to the pointers. And once you change one pointer in a bad way, you lost the list from that point onward. Forever. You cannot get to it. So that's unsafe. I'll say it in Hebrew. היתרונות של המימוש הזה, זה שזה מאוד גמיש, אני יכול לעשות מה שאני רוצה, הכל מאוד ישיר, יש לי גישה לכל אלמנט בליסט בצורה ישירה לחלוטין, אבל זה גם החסרונות. החסרונות הם שקודם כל פעם שאני צריך לעשות משהו, אני צריך לעבוד ממש קשה. אם אני רוצה לרוץ על פני כל האיברים של הרשימה, אני צריך לכתוב לולאה שעושה את זה. ואני צריך לכתוב הרבה לולאות כאלה בתור המשתמש בדאטה סטרקצ'ר הזה. לחליפין, הייתי מצפה שמי שפיתח את הליסט הזה, שהמתכנתת שעשתה את זה, תיתן לי את כל היכולות האלה, במקום שאני אעשה את זה בעצמי. חוץ מזה, יש פה בעיית בטיחות מאוד רצינית, כי יש לי גישה ישירה לפוינטרים, וברגע שאני מקלקל איזשהו פוינטר באמצע הרשימה, הלך עליי, כי מהנקודה הזאת ואילך, איבדתי את שאר הרשימה. אז הסידור פה הוא לא בטוח. Alright, so with that in mind, we will now look at the right way of building lists, and this is what we'll do from now until almost the end of this lecture. So, here's the architecture of my second implementation of lists. Well, so far what we see in this picture is what we saw before, right? We have a bunch of nodes, which are connected together, and these are objects of type node. Well, now I'm going to add the ability to look at this whole collection as yet another object, and I'm going to call this object list. This is, if you want to think about an analogy, think about a train, רכבת. The train consists of cars, קרונות. When we talk about nodes, we talk about individual cars. Every car is connected to another car, but we don't have the notion of a train. We cannot talk about a train. We can only talk about individual nodes. If you want to talk about the whole train, we need another abstraction. So this abstraction is called list. This is my train. Now, in addition to these two classes, the list and the node class, I'm going to need a third class called list iterator. And this class is something that I will discuss at the end of the lecture, so we can ignore it for now. So I have three classes, list, node, and list iterator, and I'm going to put all of them together in a collection of classes, which in Java is called a package, not only in Java, also in C++. It's called a package. And I give it a name. And in Java, the convention is that the names of packages begin with a lowercase. So I call it lowercase list. And so the list package consists of the following three classes. And the package, which is a general concept, which is unrelated to lists. You can put any bunch of classes that you want together. It's a little bit like the notion of a folder. Create a folder, you give it a name, and it's much more than a folder. But actually, in reality, when you create a package of classes, Java will actually store it in the same folder, which will have the same name. But there are more things to a package, as you will see later on. In general, why do we create a package? Because the classes in a package taken together provide some unified functionality, okay? And when I say unified functionality, I mean they serve the same purpose, some big purpose. For example, creating and maintaining lists. That's a big purpose. All right. So we'll look at each element of this package at a time, beginning with the node class. The node class is exactly the same as what we did before. Now I'm changing my example just a little bit. Instead of storing strings in the list, I store int values. That's the only difference. ההבדל היחיד בין מחלקת נוד הזאת למחלקת נוד שראינו קודם, זה שהקודמת ארגנה רשימה של סטרינגים, וזאת מארגנת רשימה של integers. זה ההבדל היחיד. Now, the other difference is that I begin the definition of this class with the statement package list. This means that this class belongs to a package which I call list. All right. And what about the list class? That's something new that we didn't have before. Well, once again, it belongs to the same package, list. And let's see how we can use this class. So I want to create a list for some reason. So I'll begin with an empty list. So I say list q equals new list. Basically, I created an object variable called q of type list, and I suppose that's a good guess that I'm going to get an empty list. Okay? I'm guessing because I haven't seen the API of the list package yet, so but actually that's what I get. Actually, this is what I get. I get a list that consists of a single node that has a 0 in its value field. And That is because this is how I decided to implement lists. In the implementation that we will show in this course, every list begins with what I call a dummy node. A dummy node in Hebrew, צומת סרק, שאין לו שום משמעות. The dummy node contains zero. It can contain anything because it's meaningless. And it's meaningless because, let's go to the next point, the last point. Users of the list, client code, never get to see the dummy node. So in this example, the list is considered empty. So I'm sure you're asking, well, so why does Shimon begin every list with a dummy node? Well, the reason is that it makes the implementation of the list operations easier, okay, in some respect. And that's why we just have to remember this detail that every list begins with a dummy node. Also, you can put there some useful information. You can put, for example, the size of the list, the number of elements you can store in the value field if you want, which is a very useful thing to do if you think about it. But I just treat it as a dummy node. All right. So what are the fields of a list? Well, a list always begins with a node object. And I call this node first because it's the first node in the list. Okay? And it has a size. So that's the second field that I may want to record about every list. So a first pointer and the size. Here's the constructor of an empty list. I start with a dummy node as I promised. So I always create a node that contains 0 at the beginning, and first is going to point at this dummy node, and the size of this list is 0. So I just created an empty list. And then I'm going to have a few more methods, of course. All right, so the first operation that I want to support is adding elements to the list. Here's the client code. I created an empty list. Actually, remember, a list that contains a dummy. And then I say add 7 as the first element of the list, and then add 3 as the first element, and then add 5 as the first element. So let's look at the list before I added 5. Before I added 5, I have 3 and 7, and it begins with this dummy node. Right? So this is before adding 5. And after adding 5, at the beginning of the list, because I do an add first, 5 will be the first element of the list, and then the rest of the list, 3 and 7. So that's an operation that I have to support, adding an element at the beginning of the list. So let's see how I do it. Here's my list class on the left. I have a list constructor. I don't repeat the code that I had in the previous slide. And now I have an add first method. Here's the signature. Adds the given value to the beginning of this list. Okay? All right. So here's the picture before adding 5. And let's see what this function code is going, what method code is going to do. So the first thing I'm going to do is I'm going to create a new node. I call it new node. And I'm going to put in this node the value that I want to put at the beginning of the list. In this case, 5. So it will look like this. I created a new node, which is a list that contains, well, actually it's a node that contains the value 5. All right. What next? Well, before I show you, I will tell you what I want to do. I want to connect the tail of 5 to 3, right? Because then the list will become 5, 3, 7. That's exactly what I want, right? So I want to connect the tail of 5 to 3. And then I want to connect the tail of 0 to 5, because the list should begin with a dummy of 0, and then the next element should be 5, right? So that's basically what I want to do. That's the surgery that I want to perform. So let's do it. Inserts the new node between the dummy and the first node. So new node dot next equals first dot next, and I will get this pointer going on, right? What is first dot next? First dot next is the value of the next field of first, of the first pointer. So I put this value now inside next of 5. So that's this micro step, so to speak. What next? By the way, notice that once 5 points to 3, the previous pointer that 5 had, which was null, is no longer relevant. I overrided it. תשימו לב שעכשיו ש5 מצביע ל3, הפוינטר הקודם של 5 נמחק. כי מחקתי אותו, הכנסתי במקומו את הפוינטר, את הכתובת של 3. Okay. Now the next statement says first dot next equals new node, right? What is new node? New node is the address of 5. So I take the tail of the dummy and I set it to 5. So that's what I get here. And the previous pointer of 0 becomes irrelevant. I just overrided it. Okay? Now notice that effectively speaking, now if someone comes in and begins to follow the pointer starting from first, what will the user see? They will not see 0 because it's a dummy. The first element that they see is 5, then they see 3, then they see 7. That's exactly what we wanted, right? We wanted to add 5 at the beginning of the list. We got it. Bingo. Now we have to do one more thing. We added an element to the list, so we have to increase the size of the list by 1. So we do size plus plus, and that's the end of the story. So I just showed you how to add an element at the beginning of any list. You know, the list can have 1 million elements in it, and I can add an element at the beginning without doing anything to the rest of the list, right? I just make a little surgery of addresses at the beginning of the list, at the head of the list, and I'm all set. So that's how you add elements to a list. Now, whenever we build a class that represents an object or objects, we expect the class builder to provide a toString method that will allow us to print or display the contents or the textual representation of the current object. So in other words, we have to discuss the implementation of a toString method for list objects. So that's what we'll do next. Let's start with the client code as usual. So here's a client code that in any class, by the way, that creates a list, and the list looks like this. I wish to remind you that in our implementation, every list begins with a dummy node which is ignored. כל רשימה מתחילה באלמנט סרק שאנחנו מתעלמים ממנו. And then the client says print q. So by convention, Java invokes the toString method on q. It's as if we wrote q dot toString, and what we get is the contents of the list, which is 537 surrounded by parentheses. אז שכותבים print q, Java, לפי המוסכמות של Java, לפי הדיפולט, קוראת למתודה toString, כלומר זה כאילו אמרנו q נקודה toString, ומה שמקבלים זה את התוצאה שtoString מחזירה. אז בואו נראה איך זה בעצם מתבצע. So here is my list class, and I'm not going to repeat the constructor that we created before. Here is the toString method, which promises to return a string that will contain the contents of this list. So the first thing that we do is we check if the size of the current list is 0. If so, we return empty set or empty list, if you will. Otherwise, we begin to build a string that will represent this list. So we set it to left parentheses, and then we create a pointer called current of type node, and we set it to the value of first dot next. In other words, we skip the dummy because we want to ignore it. So the first location of this pointer current is going to be right here. All right, the next thing that I will do is I will check if current equals null. If it does not equal null, I know that I'm pointing at a real node, and I want to see what is the contents of this node, in this case 5, and I want to append it or concatenate it to the string that represents the list. So far, this string contains only left parentheses. So I do str plus current.value, which will give me 5, and then I add a space, and then I advance current. How do I advance current? I say current equals current.next. I will get this. Well, it is still not null, so I append 3 to the end of my string. I advance to the next element. I append 7 to the next of the string. I advance to the next element, and when I say current equals current.next, current will become null. So I will get out of the while, and I will return str, and this will be the end of this method. Now, before returning str, I want to make a comment which has nothing to do with list processing, but that's a good place to make this comment. There is a problem in Java with creating a very long string that consists of many such values. The list can contain millions of elements, so potentially you're creating a huge string. Now the problem is that in Java, and we discussed it in one of the previous lectures, whenever you do plus on strings, you are creating a new string object. So it's true that the garbage collector will kick in at some point and will clean up the strings that you left behind, but still this operation takes a lot of time. So how can we improve it? And once again, this thing has nothing to do with lists. It's a general comment about Java, about working with strings. Well, the answer is that there is a special class in Java called String Builder that allows you to build strings efficiently. It has all sorts of optimizations in it. And if you use String Builder, you don't have to worry about efficiency. It will build the string without creating many strings in the process. So that's how you use it. You initialize str to be a string builder object, and then look at the while. I use a string builder function called append, which appends whatever the argument is to str, and the rest of the code is similar to what we had before. And once again, this is more efficient than simply concatenating strings. And at the end of this processing, I want to replace the last space that I appended with right parentheses. So there are functions in String Builder that allow me to do all sorts of things to the string that I build. So one of them is delete the character at the end of the string, and then I append the right parentheses, and finally I return the toString of String Builder applied to str, and this will give me the needed result. So the general comment that I like to make is that once again, String Builder is a built-in Java class. It's part of the Java class library. It's more efficient than doing plus in string processing. And when you build a long string, and here potentially, you see, we don't know what is the length of the list, right? So just to be on the safe side, we use a String Builder instead of plain, simple string processing. All right, moving along, let's talk about searching an element in a given list. So here's the same list that we had before, 5, 3, and 7. Suppose we say q.index of 7. So index of 7 or index of, we haven't seen the API yet, so I'm giving you a sneak preview. Index of looks for the first time that 7 appears in the list. And if it finds it, it will return the index of this element. And if you look at the list, 0 doesn't count. And the index of 7 is 0, 1, 2, so it returns 2. It's the third element starting with 0, so it returns 2. What about index of 5? Index of 5 is the first element in the list because we ignore the dummy, and the index is 0. What about index of 4? Well, 4 does not appear in the list, and therefore, according to the rules of the game, to the rules of index of, we return -1. So that's the example of a client code using the index of method, which is used to, one way to search elements in a given list. Let's look at the code. This is my signature, index of, and I now recall I decided not to give you the code, not in the PowerPoint. I did give it to you in the code that accompanies this lecture, and you are required to look at the code example and understand how I implemented index of. We can talk about it sort of in general form. So think about it. If the size of the list is 0, well, it doesn't contain anything, so we can return false. Otherwise, we can skip the dummy and set a pointer on the first element and check if the value of the node, which is pointed at by this pointer, by current or something, does it equal val? Val is the parameter that we were given. If it doesn't equal val, we want to move the pointer one element forward and check again. So we keep checking until we will find something. Now, if we'll find something, we'll return the index of what we found, which implies that we also have to maintain a counter, right? So we start with a counter which is 0, and then each time we advance, we do plus plus to the counter. If we find the element with the value, we return the value of the counter. And if we got to the end of the list and didn't find anything, we return -1. So you can either try to do it yourself or look at the code that I gave you, and this is how we search an element in a list. All right, the last thing that I want to discuss is how to remove an element from a list. So here once again is the same list that we are building in every slide, beginning with the dummy record or the dummy node. And now we print it, we get 375. It's not the same list, it's a slightly different list, doesn't matter. And then we say remove 7. All right, let's look at what will happen. 7 will be knocked out and the list will become 3, 5. That's the meaning of removing an element. How do we do it? By the way, if we now print the list, we'll get 3 and 5. Nice. So here's the code. This is my list class. And this is the same index of method that we discussed in the previous slide. So index of val will return the index of val, the index of the element that contains val, or -1 if it doesn't find it. And here's the signature of remove. If the given value is in the list, removes it and returns true. That's very important. It's a Boolean method that indicates to the caller whether or not it succeeded to remove the given value from the list. So the first thing that I do is I go through the list and I look for val. If I didn't find val, I return false, which means that I didn't remove anything. All right, so that's the beginning of my logic. And then if it's not -1, then I know that the element that we want to remove is somewhere in the list. Okay? Well, at that point, I start what I call 2 lockstep pointers. I call one of them prev and the other one current. And if you'll think about these 2 statements, you will realize that that's what I do. I created these 2 pointers, and these pointers will begin to go together, one after the other, throughout the list. Okay? So I check if the value of current is val. Because you see, I want to skip the dummy as usual. So I check if the value of current is null. If it's not null, I know that I have to move forward in the list and check again. So I move forward by saying prev equals current and current equals current.next. And this will effectively create this impact. And once again, I go back to the while and I check if current.value equals val. And indeed, it does equal val because I'm trying to remove 7. In that case, I get out of the while and I get to this statement here, which says prev.next equals current.next. This is like a bypass operation. See, I effectively do this. Okay, once again, prev.next equals current.next, and I skipped current. So the node that current points at is now ignored from now until the end of the program execution. You know, the list does not contain this node anymore. All right, then I do something that looks a little bit strange. I do current equals null. And you may ask yourself, why in the world do I want to do it? After all, current is out of play. I will say a few words about it in a minute. But then I also have to do size minus minus because I removed an element from this list. So this list has, one less element. And finally, I return true because I managed to delete or remove the element. And that's the end of the story. Now, let me repeat to this point, to this strange thing that I did here. Notice that once I bypass 7, it looks like 7 is out of play. But actually, current is still pointing at it. This means that the garbage collector is going to miss this node. See, the garbage collector recycles objects that nobody points at, but current still points at this object. Okay? So if I do lots of deletions of objects, and it happens, there are some applications in which you delete, you're going to create a pile, arema, of deleted objects which will not be recycled by the garbage collector. So in order to prevent this problem, whenever I don't use an object, I set the pointer to this object to null. Once you set car to null, it means that 7, this element here, this object, is not being pointed at by any object. And then it becomes a candidate for recycling. Okay? So this was kind of an optimization comment, best practice. You know, these tips, they don't look like much, but they prevent very nasty bugs. All right, so let's go on. And basically I showed you all the basic operations that I wanted to show. Actually, I want to go backward and make a few general comments. I think that for many of you, this lecture is a big step forward, because we see here programming style, which is not trivial at all. We work with pointers, which is relatively new in this course. We work with non-trivial classes that represent recursive data structures. So that's a big step forward. But that's also good news. You know, it means that you are developing as programmers, and you're seeing, you know, very important things. And if you understand about 2/3 of what I'm saying, I'm satisfied. Because the remaining third will be picked up only when you put your hands on writing code that uses linked lists, and then you will understand everything. But once again, you have to apply yourself to these abstract ideas. Also, I want to say something about comparing Python to Java. In Python, there is a built-in list element. In the language itself, you can create lists very easily, and you don't have to worry about all these pointers. And that's one reason why I don't teach Python in Introduction to Computer Science, because I think that it's very important to understand how lists are actually implemented behind the scene. You are a computer science student. You know, you're not a communication student or a business student who learns Python to write some Mickey Mouse programs. You know, you have to understand how these things actually work behind the scene. If you will not understand it, you'll have a very hard time getting into the C language, getting into C++. If you have to, and many of you will have to. So by doing these things in Java and opening up all these black boxes, you first of all understand how these data structures are actually implemented, and also you see examples of some very elegant little programs which will make you a better programmer. So all of this in the way of motivation. All right, moving along. I showed you the basic operations that I wanted to show on lists. And let's begin to wrap up. Here is the API of a typical list class implementation. We can add elements. So in addition to everything that we did, we also have many more methods, like adding a value in a particular index, in a particular location, which means that we have to make room. We have to play with the pointers in order to add this element in the middle somewhere. This useful method tells you if the list contains val, yes or no. You can get the index or get the value in a particular location. You know, what do you have in location 17 in a given list? And the opposite function, which is give me the index, the last index where val appears, remove whatever element you have in location index, set the element or set the value of the element in location index to a certain value, give me the size of the list. This is a getter. We could have said get size, but we can also say just the size. This is a very useful method that takes a list and serializes it into an array. Sometimes we want to do it for all sorts of purposes. And there may be many more list methods in a typical implementation of the list class. Now, notice that unlike the node class that we had before, the list class does not expose the actual list to the client. The client has no access to the pointers. All the processing is being done inside the list class. And that's great, because if the clients have access to the pointers, they can destroy your list. Any programmer out there who will use your list class for any purpose will be able, by mistake or not by mistake, to demolish these lists by doing something bad to the pointers. It will definitely happen if you give them access to the pointers. So the trick is to do everything without giving access to the pointers. Now here's the design challenge. Clients often want to process a list in all sorts of ways that you didn't think about. You can write so many methods in the list class, but at the end there will be a client that will want to do something that you didn't support. So what is needed is to allow the client to somehow iterate through the list and do whatever the client wants to do with every element of the list without giving the client access to the list pointers. How can you do it? Well, the answer is we can do it by providing an iterator service. And this service will allow the clients to iterate through the list, to process every element in the list without having actual access to the pointers, which sounds like hocus pocus. How can you possibly do it? Well, that's what I'm going to show you next. So I'm going to provide a method called list iterator. And this method will return an object called list iterator also, but with capital L. And this object will enable me to process the list without accessing its actual pointers. And that's what I'm going to talk about in the next 10 minutes or so. So here is the basic architecture of our list package. And there was this list iterator class that I promised to discuss, and now the time has come to talk about it. So an iterator is an object that facilitates services for iterating through a list to the client code. And here's the API of the list iterator. It's part of the list package. And it has a constructor which is given a particular node, an element in the list, and it gives you the ability to iterate the list from this node forward. אז הליסט איטרייטר זה קונסטרקטור שמקבל איזשהו צומת, איזשהו אלמנט ברשימה, ומאפשר לך לעבור לרשימה מהנקודה הזאת ואילך. There's also a hasNext method, which is a Boolean, and it simply tells the client if there are more elements to process. And finally, there's a next method that returns the next element in the list, or actually the value of the next element, and advances to the next element in the list. That's all. That's the whole API of the list iterator. Now, before we go on, I want to point out that so far we saw only concrete objects. Objects that represent bank accounts and fractions and points and nodes and lists. And you can kind of imagine every one of these objects in your mind. But it turns out that object-oriented programming allows us to also create what I call service-oriented objects, which are very abstract objects that provide operations over other objects. And this is, a little bit advanced, but what can I say? It's something that we have to teach and you have to learn. So the list operator is one of these abstract objects that facilitates action. You can do something with it over a list object. So let's see how we actually use it. The agent, so to speak, that uses the list iterator is the list class itself. And the list class itself has this strange method, list iterator, that returns a list iterator object. Now, notice how it does it. It creates a new node which skips the dummy, and this new node contains the address of the real first element in the list. And then it calls the constructor of the list iterator positioned on this new node. So the list iterator will start in the first real element of the list itself. Now let's see how we use it. So the client sees mostly the list class. Okay, the client can also use the list iterator, but actually everything that the client does goes through the list class. So the client begins by creating a list, and then the client says, I want to create an iterator over this list. So we create an ITR object variable, and we invoke or we call the list iterator method from the list class. And from this point onward, I can use the services of this iterator. So I ask if there are more elements to process, and if so, I print the value of the next element in the iteration and the space, and next is going to move me to the next element, and then I go back to my while. I ask again if there are more elements to process, and so on and so forth. So this is a very elegant and sophisticated way to go through a list without actually using its pointers. I don't see the pointers, but I can still go through the list by using the services of the list iterator. And this will print, in this case, 735, or whatever it is that the list contains. So I think that I said everything which is written here, except for the last point. If I want, as a client, I can start several iterators and use several iterators for different purposes. And I don't have time to show it, and it's not terribly important, but it's very flexible. I can use iterators in many creative ways. All right, now how is the iterator actually implemented? So far we saw only the API of the iterator. Well, the implementation is surprisingly simple. I have a current pointer that points to a node. This is the only field of the operator. And it's like a cursor. Remember the cursor that marks the position somewhere? So the current is like a cursor. And in my constructor, I set the current field to whatever node they gave me. I have to start the iterator somewhere in a particular node. So I set current to node. That's where I start. So I put the cursor right there. And then how do I implement has next? Well, I simply return whether the current equals null. If it doesn't equal null, then has next is false, right? If it equals null, has next will become true. And what about next? Well, next is a little bit tricky because I have to return the value of the current element and then move to the next element. So how do I do it? Well, I keep the value of current in a new node that I call current node. And then I advance current. I advance current to the next element in the iteration. And then I return the value of current node. I return the value of the previous element. Because that's what the API promises to do. And that's also what it's reasonable to do. So that's it. That's the implementation of the list iterator. All right. I want to end this lecture with a side comment on a very important subject called fields visibility. Take a look at this class here, the node class, and notice that the fields of node have no private public qualifiers. I'll say it in Hebrew, תשימו לב שהשדות value ו-next אין לפניהם את המילים השמורות public או private, שזה משהו שנראה קצת מוזר. מה המשמעות של זה? So what does it mean to declare fields that have no public or private qualifiers? Well, there are several different visibility options in Java, and each field and also each method in your class can be one of the following. It can be private. If it's private, it means that this method or this variable or this field is accessible only within the current class, only within, in this case, the node class. Okay? If it's public, it means that every class in the world can access this field or this method. And finally, if you don't say anything, if you don't say private or you don't say public, which is the default, it means that the visibility of the field is called package private. And this means that every class in the package can access this field. And in the case of the list package, this is very convenient because we have three classes that all manage one list. And if we'll put all the fields of all the three classes as package private, which is the default, every one of the three classes will be able to access these fields in a very simple way. And yet, users or client code outside the package will not be able to access these fields. So that's what we did in the implementation of the list package, and it works very well here, and it can serve you well in other situations as well. So this is a very general feature of the language, and we'll use it again in some of the next lectures. All right, so we arrived at the end of this very long lecture, and I want to sum up what we did with the list representation. Basically, we built a package that consists of several non-trivial classes. We have the node class that we began with, and then we added the list class. I told you that node is like representing a car, and list is like representing a train. So in Hebrew, node מייצג קרון, ואפשר לייצר הרבה קרונות כאלה, אבל אם רוצים לדבר על כל הרכבת, יש לנו את המחלקה list, שמייצגת את הרכבת. And finally, we added a third useful class called list iterator that allows the client to process the list in ways which were not anticipated by the person who wrote the list class. The list class will include many methods, but maybe clients want to do other things and they have to iterate the list. List iterator will give them the ability to do that. So this implementation allows client to create lists, to perform all sorts of operations on lists, and to do everything safely without accessing the pointers from outside the list object. So in this class, in this lecture, we talked about lists. That's the second data structure that you see here. And I told you at the beginning of the class that we can use lists and arrays for representing many important data structures in computer science. And that's what we'll do in the next lecture. And in this next lecture, I hope to be back with you in the campus. And I will see you then. And may the force be with you. Bye.